Start here. Good morning. Thursday. Thursday. Today, we're going to talk about logistic regression, which is on your quiz on Tuesday. I know. But what's nice about quiz 2 is it's only chapter 7, chapter 8, and chapter 9, right? And chapter 7 was really just a mini version of chapter 8. So it's really only 2 chapters. Right? That's some sort of, that's teacher math. So what's good about little material? I can go really deep into the topics. So quiz number 2 is, well, there's some implied knowledge from the earlier chapters, but it's really chapters 7, 8, and 9. And then afterwards, we'll do chapter 10, which is another applied chapter in modeling. Okay. And so after the quiz, we're going to do chapter 10, which is modeling in Excel. Which leaves us with Thursday next week. We've got 2 options. We can kind of keep going ahead, or you can have a break that day. Yeah. Let you think about it. We'll see. Just because to me, it doesn't really make sense to start something and then have reading break, and then I'll have to review it all again anyways, I think. Well, it's always good to ask. But then your next quiz would be huge. Yikes. I guess my next question, so you can think about that, what you want to do for Thursday. Choose your own adventure, I guess. We'll see. Yeah. Yeah. We'll see. Okay. My next question is, for the quiz, do you want me to pull from the textbook again?
Yes.
Okay. They're so basic. Or a lot of them are so basic. Like, no, I wanna build a bigger question. But I think it's kind of fair to just pull from the textbook. I will be pulling from evens and odds this time, because the only odds was very limiting. And so I know. Questions from the textbook, but we're graduating to even or odds, odd numbers. Isn't that exciting? I think there's solutions to the odd ones, right? And so if there's an even one that you're working on and you're not quite sure if you've got it, you can just send me a text and ask me, right? And so that's fine. Huh?
You're just saying we're going to text you 45.
It's fine. It wouldn't be the first time. I can handle it. I can handle it. above. All right. So any questions about, I guess, next week? Kind of nice to get the quiz over with, and then, yeah. I even built in that buffer day, thinking we'd need more time. We could use more time, but we're efficient. Logistic regression. Oh, I thought it was a question for me. No. All right. So logistic regression, I was almost gonna skip it, and then I thought, oh, let's try it. We'll try it and see how it goes. And I'll just kind of show you what you need to know about it. There's a lot going on behind the scenes, but we're just gonna build it back to the chapter 8 stuff that we were working on, so multiple regression. So it is just mapping back to regression output the way that she's laid it out. So logistic regression. Oops. Is when we have a categorical response variable. Okay? In fact, we're going to focus on, or we have to focus on just 2 possible outcomes. Okay? And so now we have a categorical response variable. Again, is it that room or this room? That room? Those guys. We have a categorical response variable. Is there even a classroom there? Weird. Versus chapter 7 and chapter 8, which we started with simple linear regression. So one explanatory variable. And then chapter 8, we built out to more than one explanatory variable, right? But in both those cases, y was numerical, right? We tried to predict y, right? And so we predict y, which we denote y hat. Oops. Double brackets here. So many sub-threads. Sub-thoughts, maybe. Got it. We're going to predict a categorical response variable, and for logistic regression, the response has to be just two possible outcomes, right? So a binary variable. The response is a binary variable. Oops, I should clean that up. It's kind of important. Zero, one. Success, failure, that kind of thing. We can create a lot of binary variables, right? If you're interested in something, then everything else is a failure, right? And that one thing is your success. So if you're rolling a die, for example, and you're interested in the rolling a 6, for example, right? Then even though there are other outcomes, 1, 2, 3, 4, 5, right? If you're not interested in those, you could call those not a 6, right? And so you can create binary outcomes. We can create binary outcomes. Right, where, for example, a success might be rolling a 6. Have a 6-sided die. And a failure would be not rolling a 6. Right, 1, 2, 3, 4, or 5. All of those would be denoted as a failure. So a 0 in your in your data set, right? And so 1 is a success and 0 is a failure. So what we're going to have is kind of a yes, no, success, failure outcome. Okay. Now, this is where I kind of, can she pull it off? She does. She avoids a lot of theory. And I'm going to try to as well. But we understand that if I roll a die, then some proportion of those rolls will be sixes and some proportion of those rolls will be not sixes, right? And so we're going to have some proportion of successes. Okay. So in a number of trials, we will have a proportion of successes. What's kind of interesting though is a proportion is the same as a probability, right? All those P's mean the same thing. So a percentage is a special version of a proportion or a probability, right? And so this is a probability. Okay? So now we're going to interpret this proportion as the probability of success. Okay? And so this becomes the probability of success. An interesting leap. Oh. And we're going to denote this probability of success by p hat, denoted by p hat. P for probability or proportion, if you prefer, right? And then the hat is doing the same thing. Now it's a predicted probability. Okay. And so this is your predicted probability of success. Let me squeeze that in there. Ugh. So what happens is, okay, if we have some y here, and let's just focus on one x variable because otherwise it becomes very hard to draw, right? We can try to draw something 3D. I'm not very good at it, am I? Well, we can try there, something 3D, but that's where we max out, right? And so 3D is what we would need for 2 explanatory variables. And then you would need 4D for 3 explanatory variables, right? And so on and so forth. And we just can't see that, right? And so, but it can happen mathematically, okay? And so if we have a y and an x here, now this is going to be the response variable, right? And so it is on a scale, but really your only 2 options here are 0 and 1. Let's plop those down there, right? Even though there's some proportion or probability of success, right? There are only 2 outcomes, right? 2 possible outcomes. We're forcing that. And so usually what we get is we get data that kind of looks like this. So we have some zeros and then we have some ones. And if we fit a straight line through this, sure we could, but we're missing a lot of action here, and a lot of our predictions would be wouldn't be outcomes, right? And so what we do instead, or what happens, is we kind of fit this curve that looks like this. through some math. But we're going to be able to straighten this thing out. And so, or at least that's what we're doing in our calculations. So what happens is once we transform this thing, we have a transformation. I'm just going to grab it from here. We're going to get to look at experimental data today, which is kind of fun. We never get to see experimental data. What does that mean? It means we could draw conclusions about causation, right? And so that's kind of interesting. It's hard to set up an experiment like this. So what happens is we do a transformation, okay, on these probabilities or these proportions. Okay? But then this looks exactly like what we had last day, right? These are the betas. This is for the population. Okay. And so here, this is just multiple regression for the population, which means we're going to be able to use multiple regression output. We just need to do a little bit more work with it. Okay. And there's a lot of theory, I know that, but I'll focus on the things that you need to know. But here we're just building up to it, right? So you don't need to know how to do this yet. I'll be clear when you do. So, okay. The transformation that we do is the logit transformation. Okay. I'll grab that. So this transformation is log base E. Uh-oh, flashbacks to logarithms. I know, yikes. Of that proportion over 1 minus the proportion, which kind of as a side note are the odds. And so sometimes we call it the log odds, but we can call it the logit just for simplicity. And so here, the transformation is called the logit, or the log odds. This is log base E, which we usually write ln, right? It's to emphasize something later on. Let me see here, bump that up. Okay. If we want to solve for P, now this is math that we can do. I know you can because we did it last year. And so let's do that. Let's do what we can do. Treating this all as one thing, right? Just kind of group it all together, and that will give us some one value, right? Some prediction. Okay. And so this will be one value. Okay. If we have to solve for PI, P subscript I, the probability associated with the ith observation. Okay. The probability of success for the ith observation. Okay. We write this out. One value. Let's call it let's just call it, I don't know, capital B for all the betas. Just something, right? Just temporarily. And then once we're done manipulating this thing, because I don't want to write that out a bunch, right? And so capital B is going to be a placeholder for this whole thing, okay, which we will be able to just calculate a value for from the outcome or from the output. Okay, so we have log base E, and I want to highlight that it's log base E, so I'll keep writing it like that. Pi over 1 minus Pi is equal to B. We're trying to solve for P subscript I. What do you have to do? You're gonna have to take e to the power of both sides, right? To get rid of that log base E. Okay, so then we get e to the power of log base E of Pi over 1 minus Pi is equal to e to the power of B. We did that so that this could drop down, right? I still have e to the power of B, so e to the power of that mess on the other side. That's okay. That's e is just a number, right? And then that mess is just a number, so it's really just kind of the same as 2 to the power of 3, for example, right? It just looks really messy. So from here, now I have Pi over 1 minus Pi. And if you don't want to draw, write the i's, if they're confusing to you, then you don't have to, right? They're technically there, so I'm going to continue, but is e to the power of B. Maybe I should write this a little bit better. Okay. We want to solve for P, right? What would you do? You'd have to multiply this over here, right? And kind of expand this thing, right? And so that's our next step. And so we get Pi is 1 minus Pi times e to the power of B. Or other way around, doesn't matter. Okay. Then, what do I get? If I'm trying to get all my p's on one side and everything else on the other side, I have to expand this out. And so I get Pi is 1 times e to the B. E to the B. Sounds cool. Minus Pi times e to the B. It's like that song. If you don't know me, I'm M to the B. Maybe. Hey, that's my, there you go. That'll be my first hit song, my first hit stats song. E to the B. We're so close to extracting this P, right? If I move this P times e to the B over to the left-hand side, can't unhear it now. Pi plus Pi times e to the B is e to the B. Okay. I can extract a common multiple of P, 1 plus e to the B is e to the B. Solving for P then, I get e to the B divided by 1 plus e to the B. Whoo! I guess the question is, do you want to derive it on the quiz, or should I just give it to you? I mean, this is a fun math exercise.
Yeah, I like that.
Yeah. It's just solve for P, ba, 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 e to the B. It's kind of fun, I think. I'd let you start here. I'd give you this. Say solve for P. Anyways. I doubt they make you do it in the textbook, so probably not. That'd be rude. So I'll need to give it to you, but that's where it came from. Okay. Now the B's, we avoided writing it all this time, but really PI is going to be e to the power of beta 0 plus beta 1 x1 plus beta k xk, right? Allowing for k explanatory variables. Over 1 plus that mess. 1 plus e to the beta 0 plus beta 1 times x1 plus plus beta k xk. This would be the model for P for the population, right? And so this is the population P, or the population probability of success. We don't have the population. So that's how we're going to get our P hats. And so since we only have sample information, that's how we're going to get our, I guess I'll keep the same color, P I hat, right? Prediction from our sample is, it's going to look very similar, but e to the b0 plus b1 x1 plus bk xk over 1 plus e to the b0 plus b1 x1 plus bk, oops, not just k, bk xk. These two numbers are the same, right? And so we can find these, right? These values are going to be the same. Found by finding the predicted value for the ith observation. The ith. It's just a placeholder. So the ith is either the first, second, third, fourth, but you have I observations, just generically. That's what this I is for. Yeah, so I goes from 1 to n. And it's just your row number. So the ith observation. So the same values which are found by calculating the predicted value for the ith observation. Looks bad, but it's not really. We'll introduce the data and then we'll jump to the output and we'll do some work. Okay. So, but any questions before we do? We'll come back to this. but we already sketched this graph, right? We have 0, 1 outcomes, but there's going to be some probability. In general, right, if the probability of a success is more than 50%, you can adjust that cutoff, right? But in general, if it's higher than 50%, you would say, hey, I predict that's going to be a success. And if it's less than 50%, you predict it's a failure, right? And so there's this cutoff. But where's the data? So what they did is they conducted an experiment because they suspected that there was discrimination in hiring. And so this is from 2003. That's kind of interesting. And so they're looking at the effect of race and sex on job application callback rates. We understand if you send out an application, the overall probability that you get a callback is kind of low, right? That's why you send out lots and lots of applications, right? But they were concerned because they suspected that the callback rate was affected by race and sex, right? Which you're not allowed to do, it's laws. And so they did a lot of, it's a complex experiment. We've simplified it, but it turns out that the results aren't affected by the simplification, so it's fine. So it's fine. No, but they did that to make sure, obviously. And so what they did was they made up resumes, right? They just created a bunch of resumes and they picked names that would imply race and gender, okay? And so, and there's even a note, they did a focus study on, did these names, imply what you think they're going to imply, right? And so, you hear Lakeisha, you think that's a Black woman. And if you hear Greg, you think that's a white man, right? And so that's the example. And so, so that's kind of that's like a sub study, right? Where you have to pick names where both the race and the gender would be clear just from the name, right? And so they made up these names and then they have this implied race and gender. Okay. So whether they received a callback, right, is a yes/no situation, right? And so you either receive a callback or you don't. And they only focused on 2 cities, right? And they did introduce blocking. So they did send, I think they said 4 resumes to each job application, right? Just to kind of spread it out. And on each resume, they have an indicator for a college degree, right? Did they say they have a college degree or no? Years of experience, right? So they're just making this stuff up and they're randomly assigning all these things. Okay. Let's see here. Honors, an indicator for the resume listing some sort of honors, employee of the month. Not just academic honors, but any honors. Military, right? Did they list any military experience? And the email address, I think, is kind of interesting. I don't know why you wouldn't put an email address on your resume, but I guess they decided to exclude it for some, right? Which is kind of interesting. Do you think you'd get a callback if you don't put your email on there? I don't know. I guess yeah, that's good. It was all Hotmail back then. I still rock my Hotmail. I think it's cool now. It's like back to being cool, I think. I was able to hang on to my Hotmail for so long. Yeah, such ridiculous hotmails, but don't worry, my hotmail is normal. I've had some weird ones though. I rot you stinky potatoes was one. That's weird, right? We're all, yeah, kids. And then the race, which is the implied race from the name that they've listed, and then the sex of the applicant implied by the first name, right? And so that's why it was so important that we have these kind of names that imply both race and sex. Okay, so I didn't want to take up too much room there. So they've got all the names, 36 names, and their implied race and their implied sex, and it's kind of cute, I think. But that's not what we're here for. We want to predict the probability of a callback, right? Relying on these indicators, right? As well as other information in the resume, right? It's possible that it was just the information in the resume and that would be a relief, right? And so here we go. We need some output. Do you want to start with just one? Fine. We'll start with just a simple linear regression that looks like this. This looks like what we're used to seeing, right? And so here, this is just a y equals mx plus b situation, right? And so here we've got our b0 plus b1 x1, right? If there's only one x, then we usually don't write the 1, but. And here honors is a 0, 1, right? They either have honors listed or they don't, right? And so I don't think so if it's an indicator, it's a 0, 1, right? Honors, which is an indicator, which is 0, 1. Oh, weird. So we can predict, if you just kind of ignore this side for a little bit, right? We can use this to predict the outcome if we have honors listed or if we don't, right? And so if we let, let's see here. If we let honors be 0, so no honors listed, then this is our B, right? Our big B. Right. So then if we call it big B, Big Bertha. B is going to be negative 2.4998 plus 0.8668 times 0. That's a number, right? Times 0, that's easy enough. Even I can do it, negative 2.4998. I don't want to predict the log base E of P hat minus over 1 minus P hat, right? I want to predict P hat, right? And so to calculate P hat, I'll put the ith P hat. That's going to be e to the b over 1 plus e to the b. So then my predicted probability of a callback is e to the negative 2.4998, realizing I cannot do that in my head, over 1 plus e to the negative 2.4998. It's just a number. It's just a number. In fact, it's a number between 0 and 1 because it's a probability. Probabilities have to be between 0 and 1. So e, oh, not pi, e to the power of, and did they change your buttons? The e on mine is in the alpha menu. Just kind of.
We also do have an e to the power of the natural log key, shift natural log.
Hey, there she is. I'll use that. I even told my class this year that you read the instruction manual for the calculator. Like, here's a wild and wacky thought. Could read it. Divided by 1 plus e to the negative 2.4998. Using brackets, I get a pi hat of 0.07587220195. Is that what you guys got? What's this? If we build a model only incorporating if there was honors listed or not, okay, and that's all we've incorporated, okay, then if you don't list honors, the predicted probability of getting a callback is 0.07587, right? Or roughly 7.6%. Low, but that's kind of, you know, what we're expecting anyways. We're expecting a low-ish rate for your callbacks overall. Okay. And so here, therefore, using a model which only considers honors, it's kind of painful to spell it like that, but it's okay. It's to match the variable name. We predict the probability of a callback for an individual who does not list any honors is this. For an individual who does not list honors, we predict the probability of a callback for an individual who does not list honors is 0.07587, or roughly 7.6%. You can bring it back to the percentages. It's easy to think, it's easier to communicate percentages, especially when you round it to just one decimal place. Cheeky. Okay. What about someone who does list honors? Can do that, all right? And so now, what about, I want to say person, but it's really just a resume that lists honors. I almost drew a pseudo U in there. then if we think about it as our B, all right, just kind of lumping it all into one. B, we were told that, okay, B is this, but now I'm going to turn honors on, right? A categorical variable. I'm going to flick the switch and turn it on and see what happens. I'm gonna, so I don't have to remember it. I'll match the color and turn this into a 1. Now, that I can't do. 2 point, well, under pressure. Plus 0.8668, I get a B of negative 1.633. The B is really a kind of a Y hat, but it would be too confusing to incorporate Y hats into this. So I think calling it big B is pretty fun and easier. Okay. So now we can find the predicted probability of a callback for someone who does list honors. Pi hat is e to the b over 1 plus e to the b. Okay. Oh. You've committed, you're stuck now. Bye, Danny. He can't get enough. He's not in this class. He just wanted to see what was on for today. All right. So, in fact, he's not in any of my classes this term. Anyways, can do this math again. Right? This math is not bad, right? Especially if you have this p hat formula already kind of pre-baked. So e to the negative 1.633 over 1 plus e to the negative 1.633. E to the negative 1.633 divided by 1 plus that answer. I got a way bigger. I got 16.3%. Wow. 0.1634198,057. Right. Only incorporating your honors into your model, right? We have other factors that will incorporate, so then that'll take some of the pressure off of whether honors were listed or not. But clearly it does make some sort of difference, right? We jumped from 7.6% to 16.3%, right? That tells me you should just make up some honors and put it on your resume. No, maybe not. There's that would be abusing the stats, I guess, but there you have it. So therefore, the predicted probability of a callback for a resume which lists honors, or a resume which lists honors is 0.1634, or roughly 16.3% ish. How about I toss a 2 on there? Good measure. Capture all the activity there, or roughly 16.3%. So 50% in this case, right, might be too high in terms of classifying it as a potential success or failure, right? And so maybe it's reasonable, but I think, you know, maybe over 15%, you would classify it as, okay, I predict that this person will get a call back, right? And so, right, you can adjust that, that threshold. We're not going to do any classification, but that's what it's leading into. We're just going to stop at the probability of a callback is this. Okay. Okay. I was going to go back to the graph, but maybe the graph isn't very helpful in this case. Your output, which we're not going to talk about how we get this output, right? I'm just going to give you output. This looks exactly like the multiple regression output that we talked about last day, right? And so we've used it before, right? In fact, we called it the full model. The full model is the model that incorporates all the predictors, all the explanatory variables that we have. Okay? And so we know what this looks like. And for us right now, we're just going to focus here on the estimate, and we kind of ignore the rest for a good long while. Okay? We'll bring it in if we have time. Okay? But we know how to read all this output. We have the intercept, which, remember, incorporates all of your reference levels, right? And so for the job city, this one is Chicago. And so job city Chicago means that if it's a 1, it's Chicago. Wait. And if it's a 0, it's Boston, because we only had two cities that we were considering, right? And so if the job city Chicago is on, it's Chicago, and if it's off, it's Boston, right? College degree 1, right? Means that yes, there was a college degree listed, and if I turn it off, then there was no college degree listed. Right? So far, just categorical binary variables, right? And we haven't had to generate more levels like we had last day. Years of experience is the number of years of experience, which is the numerical variable, right? And honors 1, right? If it's on, they have honors listed, and if it's off, they don't have honors listed. Okay? Military 1, if they have military experience listed, then it's on, and if they don't, it's off, right? 0, 1. Yeah.
So is that saying having a college degree lowers the probability of getting a callback?
Does. But
just checking to make sure I'm not totally
it does. Yeah. So it means that, so you start at a negative, so all the default levels are also negative, but Chicago brings it down. So that's bad. Don't apply in Chicago. Yeah, having a degree brings it down. Listing military experience brings it down, which is kind of counterintuitive, right? But don't worry, you can counterbalance it by adding an email address. What's important to remember is, yeah. what's important to remember is that these coefficients are only going to be these coefficients if all of these other things are in play. Okay? And so if you remove one thing that might be taking things over, like the has email address, it's possible that these things would kind of sort themselves out and become what you think they should be. They should be positive, right? And so, right, and maybe the years of experience should have a little bit more impact, right? Maybe, just a thought, right? And so these are all kind of wonky, but it's because all of these, when we interpret these coefficients, right, it's assuming all the other things are held steady, right? And so assuming all of these other variables are in there, then yes, listing a college degree will decrease by a little bit, right? It's not going to decrease your probability. So that's why I didn't say probability, right? Because what the probability does, hey, we just might sort this out after all. Let me think about this. No, it's still bad, I think. Because these are B's, right? Our B's come from this output, right? And so our probabilities link back to the B's, but not directly, right? And so what we're really looking at and what we're talking about from these coefficients would be our B's, right? And so as the B's here went from they're increasing, still not good, is it? Still doesn't make sense. As the B's were increasing, our probabilities also increased, but not directly across. Well, let's see what happens. Where were we? Race. You're white. 1. You're a man. Down. Let's find a predicted probability for someone who has, for one of these resumes, right? And so, and I'm gonna steal it because they've got it written out. Okay, I guess I should mention, although it's not really gonna come into play for us, the Akeki information criterion, you wanna have a lower Akeki information criterion for a better model. What's tricky is it's just relative to other models. And so we don't need to use it. Just understand that that's how it's been picked. Okay. They dropped the college degree. I have to use this new output. I'll make a little note here, just in case it comes up in the questions that you're doing. And so for logistic regression, we use Akeki, the Akeki information criteria. Akekis? I'll have to look. Information criterion, which is called AIC, to select a model, okay? unlike the R squared. But if we think about R squared, well, it's related to the correlation, and the correlation only applies to linear models, but we saw that curvature, so we don't have a linear model anymore. And so that's why we need some other criterion. But I want you to focus on the R squared, but just know that for logistic regression, we use the AIC, and the goal is to lower the AIC, as opposed to R squared, where we were aiming to get as high of an R squared as possible, right? Capture all the information. And so the model with the lowest AIC from the full model excludes college degree, which is kind of funny. From the full model excludes college degree. We don't know what types of jobs they were applying for, right? It's possible that these were jobs where you don't really need a college degree, and so that's why it was kind of making things wonky, right? It's always kind of frustrating. I remember looking for summer jobs, and they wouldn't give it to me. You can't, you don't want this job. You're way overqualified. If I'm applying for it, I want it. It's so frustrating. It's been a long time since I've had to apply for a job, but it's the worst thing in the world, I think. And so I don't envy you guys one bit. It's what made me keep going to school. I don't want to apply for a job yet. Just keep going and going and going. It's the worst thing. So we don't know what jobs they were applying for. So maybe the college degree was kind of muddying the waters a little bit and not giving us very good predictions, right? So now we've removed it, and now we have some new estimates, right? Being a man is still working against you, but and I guess the military experience, I don't know why, usually that's a good thing, but especially in the States, they love that stuff.
Get a football scholarship though.
And don't apply in Chicago. Which means the intercept incorporates what? Jobs in Boston, right? No honors, no military experience, no email address, Black, and female. That's the intercept, right? So here, the intercept describes a resume with, can I just grab these so I don't have to write them all out? Job city equals Boston. Years of experience is 0. Okay. Honors 1 is 0. Military 1 is 0. Has email address 1 is 0. Race white is 0, which means it's Black. And sex man is off, which means it's a woman. that's incorporated into the intercept. Now from the intercept, right, we make adjustments depending on our individual observation, right? And so now, now we're ready to make a prediction. Let's see here. Fine. Clean that up. This is all I really expect you to be able to do, right? Is if I give you output like this, then you should be able to predict the probability of a success for that person or for that resume, let's call it. So use the model summarized in, this is table 9.6. To estimate the probability of receiving a callback for a job in Chicago, where the candidate lists 14 years of experience, no honors, no military experience, includes an email address, and has a first name that implies that they are a white male. Call him Greg. Okay, so now we can use the output to calculate our B, right? That's our first step, is finding this B, which we find from our output. Okay. And so for us, B is not a technical thing, but I think it's working out for us. So you can call it B and that I'll know what it means, right? And so B is this thing. Oh, I need to, need to have it all on the same page here. I'm just temporarily going to put it down here so that I can see it. Because our B is negative 2.72. It's funny because I am putting my hand over it, so I can't see it, but you can see it. There. Negative 2.72 minus 0.44 minus 0.44 times Chicago. I should write job city underscore or underscore Hotmail. Job city subscript Chicago, but can just get a little bit lazy and call it just Chicago. And so plus 0.02 years of experience. So just call it years. Plus, where am I? Honors, 0.76 times honors. To indicate that this calculation keeps going on the next line, you usually do a little bit of an indent, right? So it makes it easier to read. And so now 0.76 minus 0.34 times military plus 0.22 times the email plus 0.44 times white. And can I sneak it? Sure, I'll decrease my indent. Dink. Minus 0.20 times a man. Now I can delete that. So use the model summarized. That's what we're doing here. Right? But now we want to find the predicted probability of receiving a callback. Now we've got specific things to enter into our explanatory variables. And so B is going to be, because I can, I'm going to copy paste. Job in Chicago turns this into 1. 14 years experience turns years into 14. No honors, so we can turn that off. No military, turn that off. Includes an email address, 1. And has a first name that implies that they are white and male, turning both of those on. Okay. Pretty cool. Let's see what we get. It's nice because a lot of these are just ×1 or ×0, and so you don't really need to do the multiplication, right, in your calculation. -2.72 minus 0.44 plus bracket 0.02 times 14. That's the only kind of curveball. Then we're back to +0, +0, plus 0.22, plus 0.44, minus 0.2. I get a B of -2.42. No? Did I do something weird? Did you guys? Yeah. Okay. Careful with your negatives. Negative on Chicago and the man. So now you can take this B, you can calculate the predicted probability of a callback for that resume, e to the B over 1 plus e to the B. E to the -2.42 over 1 plus e to the -2.42. E to the power of that divided by 1 plus that. I get 0.08 166025546. Therefore, the predicted probability of a callback is 0.08166, or roughly 8.17%. I know, inconsistent. Nice. Can't remember if there's another one to do. Can do an example from the textbook. What if we do the same thing, all the same characteristics, but now we have a black male instead. So the only thing that's changing is the race. So now we get a different number for our B, which changes our probability, but we want to know by how much. So now let's see here. Everything else stays the same, except now we're going to turn that into a 0. Then I get a B of 2.72 minus 0.44 plus 0.02 times 14, all the same, plus 0 plus 0 plus 0.22 plus 0 minus 0.2. I get a B of negative 2.86. I'm noticing in the textbook they have more decimal places, but that would be because they have the actual model output and we're only seeing rounded values. And so that's why we have nice kind of clean numbers. So now our B has changed, I hope, from negative 2.42 to negative 2.86. And so we want to know how is that going to impact our probability of a callback. E to the B over 1 plus E to the B. I get 0.054166700048. Which is lower. And it's important that this is an experiment, right? And so, because then we can talk about causation, just like we learned in the first chapter, right? And so now, kind of a gotcha for these employers with the fake resumes, but I don't know. They talk about how difficult it is to kind of pinpoint certain employers, right? This is just employers in general. So still difficult to prove. But let's see here. So therefore, the predicted probability of a callback is 0.054167, let's call it there, or roughly 5.4%. I guess I should keep the same number of decimal places. Fine. 5.42%. That difference, as we'll see in the coming chapters, right, could be due to chance. And we're going to have tools where we can compare these numbers and see if they're significantly different, right? And so we still have kind of some work we can do with this, but for now, right, just being able to predict those probabilities of success is all I want you to be able to do and need you to be able to do from this chapter. It does go on, and only because I find it interesting. I'll put it in here. But the expected, running out of time. That's how I know. the expected number of resumes that you would need to send out in order for one success, and this is going back to a geometric distribution, which we're not going to talk about, but how we calculate it is 1 over the probability. Yeah. And so this is not something that I'm expecting out of you, but just to compare the two, right? I find it's interesting. And so we can use these probabilities that we found, right? They've got slightly different values just because they have more decimal places, right? And so, right, if you've got a first name that's perceived as white, then your probability of getting a call back was 0.0835, which means that roughly 12 jobs you would have to apply for in order to get a call back, right? In order to expect a call back. Okay. That's still a lot, right? But then when we look at, okay, so you've got a name that is perceived as black and everything else is the same, right? And so now we can compare these two. You would need to apply to about 18 jobs on average in order to expect a call back. Yeah. I'm going to change this to expect a callback. Right, just playing the numbers. Right. It's not guaranteed, right? But once you've hit 12 jobs or 18 jobs, then you're expecting one of those to stay. Yeah. And so, right, kind of interesting to compare those numbers. 12 to 18 is kind of a huge jump, right? And so, there's also a problem for groups of different sizes. And so if you have, let's do this one. And again, just to broaden your perspective, I guess. If you have a company that has 20% women and 80% men, right? And we'll assume that this is a very large company, 20,000 employees, right? And so now we've got this kind of solid spread and distribution, and we know 20% women and 80% men. And so, of course, other gender identities, but let's, we're only focusing on these. And so, suppose when someone goes up for promotion at the company, 5 of their colleagues are randomly chosen to provide feedback on their work. Okay. And so now, okay, the next step would be, oops, hey. I'm just gonna grab it all. Should have just grabbed it all from the get-go. Imagine 10% of the people in the company are prejudiced against the other sex, right? That can happen. So 10% of men are prejudiced against women, and similarly, 10% of women are prejudiced against men. Okay, fair enough. It's 10%, so it's relatively low, right? But it happens. Who's discriminated against more at the company, men or women? So if you have 100 men who came up for a promotion, right? Then the company goes out and asks 5 people per man, right? Hey, what do you think? Should he get this promotion or what? And so for these 100 men, right? 500 random colleagues will be tapped for feedback, right? Should this guy get a promotion, right? And so of those 500 random colleagues, we expect 20% of those will be women, right? Making 100 of them women. Now, of these 100 women, 10% of them they're expected to be biased against the man that they're reviewing, right? So then, of these 500 reviewers, okay, they're gonna see 10 out of those 500, which is 2% of those colleagues that are discriminating against them, right? They're gonna feel that 2%. Okay? Whereas if you have 100 women who have gone up for promotion, same thing, right? You have 500 random colleagues giving feedback, okay? And 80% of those, so 400 will be men. Okay? And so just looking at the gender distribution at the company, right? 80% will be men. And so of these men, of these 400 men, right? 10% of 400 is 40. So all of a sudden you have 40 out of 500 that are biased against this woman, or these women, I guess. Does anyone remember Binders Full of Women? No. Anyways, it was in a presidential debate where Mitt Romney was trying to convince, oh yeah, we're hiring so many women, we got binders full of women. And it just, yeah. It wasn't, it didn't play as well as he kind of hoped it would, I think. So it's got binders full of women. And so I can't remember what year that was. Yeah, was it 2012? Yeah. So now, right, 8% of the colleagues hold bias against these women. And so even though everything kind of looks even, right, if you've got an uneven distribution, right, in your population, right, which applies to a lot of things, right? Could even bring it back to water samples if I was thinking on my feet here, right? How could you do that? There's kind of something rare, right, that you're trying to measure, right? Be the same thing, but this 2% versus 8% is just kind of interesting. Interesting. What do you do? I don't know. There's no solution that stats can give us. It's outside the realm of stats. Okay. Can do one more. I didn't pick one. Let's do this possum classification. We've seen these little guys, right? The possum. A logistic regression model was proposed for classifying common brush-tailed possums into their two regions. Right? And so there are two regions, and I guess Victoria is one of them. This is in Australia, but Victoria is one of them, and 0 is not Victoria, I guess. I don't have enough information in this blurb. So not Victoria. Probably just outside Victoria. I wonder where Victoria is in Australia. Anyways. Southeast. Oh, okay. Nice. Southwest is kind of a different story, I guess. It's probably a lot of possums there though. Okay, so we want to predict which region they came from, right? And so a success is if they came from Victoria, and if it's a failure, then we're just calling it not Victoria. And so we've got this output, right? The intercept, we've got the sex male, so that indicates that's an indicator variable that is 1 if it's male and 0 if it's female, right? Which means that the female is in the intercept, right? The skull width is numerical, and so that's kind of nice. So for every increase in skull width, we expect a decrease in B for representing Victoria, right? And then the total length is numerical and the tail length is numerical. So for A, write out the form of the model. Let's call it B, is 33.51 minus 1.42 times male minus 0.28 times the skull width plus 0.57 times the total length minus 1.81 times the tail length. So there's our model. From here, right, also identify which of the variables are positively associated with the outcome of living in Victoria when controlling for other variables. And so now, right, the only positive one is the total length, right? And you can just read it across. We don't have to worry about those probabilities because in fact, the B's we found behaved the same way as the probabilities, just not on the same scale, right? And so, so a higher B gives me a higher P, right? And so then the total length is positively associated. Total length is positively associated with Victoria. Suppose we see a brush-tailed possum at a zoo in the US and a sign says the possum had been captured in the wild in Australia, but it doesn't say which part of Australia. And you say, man, I really wish I could predict if it's from Victoria or outside Victoria, and you can. However, the sign does indicate that the possum is male. Its skull is about 63 millimeters wide. Its tail is 37 centimeters long, and its total length is 83 centimeters. And what is this is the reduced model, but you don't need to worry about that. What is the model's computed probability that this possum is from Victoria? And don't worry about how confident you are. Slim it down a little bit. Okay. So from our model, we've got some inputs and we can calculate, whoopsies. We can calculate our B. Get myself some room here. Okay, so the sign says it's a male, so that turns it into a 1. It's got I should read it off here. Its skull is about 63 millimeters wide. I'm gonna go ahead and assume that all these units are the same and you are allowed to do that as well. Its tail is 37, hey. Its total length is 83. Curveball and the tail length is 37. Right. Careful about those two. They didn't come up in the same order as our model. But besides that, we're okay. Right? Can calculate B. So B is 33.51 minus 1.42 plus 0.2, oh, sorry, minus 0.28 times 63 plus 0.57 times 83 minus 1.81 times 37. We get a B of negative 5.21. So then the predicted probability of them being from Victoria is e to the b over 1 plus e to the b. Oops. Which is e to the negative 5.21 over 1 plus e to the negative 5.21. E to the power of that divided by 1 plus that 0.005432 1. No, kind of 0, 1. Right? 1, 2, 3. Scientific notation. Therefore, the predicted probability that the possum is from Victoria is 0.005432 or 0.54%, right? Very, very small. The predicted probability that the possum is from Victoria is 0.005432 or roughly 0.54%. Right? I would say it's unlikely that it came from Victoria. Right? Here, I would want the probability to be much higher, probably higher than 50% for me to be able to say, okay, I would say this possum came from Victoria, right? And so in general, we would classify a probability greater than 50% as a success and less than 50% as a failure, right? Because there are only two possible outcomes. So you can talk about the probability of success, but then if you take a step back and you think, okay, if the probability of success is 0.54%, that's really, really low, right? And so then you would say, okay, kind of unlikely that it came from Victoria. It's more likely that it came from not Victoria. In general, we would classify a probability greater than 50% as a success. And of course, the follow-up and less than 50% as a failure. I don't think I have time to pick another one and do it. We can though. Nah, I think that's good. Got more in the textbook to do if you want. If you have any questions, let me know. One last question for you though. There's going to be an online assignment for this stuff. It is on the quiz, so I was going to make it due before the quiz, force you to do it. Or do you want me to extend it over reading break, and then it can haunt you over reading break? All right, but it is on the quiz, so
Our next quiz is.
So the quiz
the
is
week
79.
right after we break, the Tuesday.
it's on next Tuesday.
Next Tuesday.
Yeah, Tuesday. Yeah, yeah, next class. Oh, that sounds nasty. No.
We could do like a half hour of Thursday before.
Don't have that, no class Thursday.
Well, I was waiting to hear back on what you guys wanted to do.
Wait, what? I was.
So for Thursday, I had it as a buffer day in case we needed more time to kind of figure things out. But we can all be sick on the Thursday next week. Or just because it's hard to introduce something and then have a week and a bit go by, and then we'd have to kind of reintroduce it anyways. So then kind of a cleaner cut.
Yeah, so next week is one day has two, gets two lab reports, two formal lab reports, and two lab reports.
I guess I can stop this recording.